All right, this is going to be our notes on electromagnetism. So this is page 6 of your packet. So if you're not on page 6 right now, make sure to get to this page and follow along on your packet as we go through this. Now, you guys will be pretty happy to hear there are no math problems in this set of notes. So we're leaving the math for the last set of notes and moving on with just some definitions here. So electromagnetism, you'll notice it's all one word. And a lot of times we think about electricity and magnetism as two different things, but really they are kind of the same thing. So that's why we combined it into one word here. And so we're going to start off with a definition of a magnetic field. And we're going to start off by drawing a magnet at the bottom here. So this is going to be a bar magnet, which we saw in class last time. Bar magnets are split into two sides. Typically they're red and blue. So one side is going to be called the north side, or the positive side. And the other side is the south side, or the negative side. Now, when we draw our magnetic field lines here, we draw from north to south. North to south. So let's see what that looks like with lines here. So we're going to curve our first line up and around. And we're just going to have a bunch of lines that are kind of going around the magnet from north to south. Like that. And we'll do it along the bottom as well. There we go. All right. And even though these lines are connecting, we also have some magnetic field lines that kind of just go out, that aren't quite going to connect all the way around. And we'll have some coming in for the south side too. All right, so these are the lines around our magnet that make up the magnetic field. And so for our definition here, these lines are not visible to us when we look at a magnet. Even though they're always there, these are invisible. So we're going to say that these are the invisible lines around magnets that can push or pull. So in other words, it can do a force, charges without touching them. So the magnet itself doesn't need to touch it, it just needs to get close enough for these magnetic field lines to be able to move charges around. So with this definition in mind, let's look at some practical applications of electromagnetism. The first part we're going to look at is electric current. So this is a very basic circuit here. We've got a battery and a light bulb, and it's connected by wires. So this is very similar to what would work in your house to turn on a light. You just got to flip the switch and then the electricity will flow through. We can think about that flow of electricity kind of like water through a pipe. So our definition for electric current, we're going to call it the flow of electricity through a wire. And a good analogy here is that electrons flow through the wire like water flows through a pipe. And so when you flip this switch, the electrons are going to start traveling around the wire, and as they go through the light bulb, they will transfer their energy, and that's going to turn on our light. Okay. So we need to know about electric current to be able to know what to do in the next part here. So you might have heard of these things called electromagnets. So a normal magnet is always magnetic. An electromagnet only works when it has a current flowing through it, so when there's electricity going through it. So for our definition for an electromagnet, when current is run through a wire that is coiled. So you'll notice that our wire is all coiled up here. It acts like a magnet. So you can do this with anything if you coil it up enough. But when electricity runs through this wire and it's spinning around like this, it's going to actually create a magnetic field. So this whole thing becomes kind of like a magnet. So the left side will be positive, the right side will be negative, and we'll get those lines, so north and south. We'll get those same lines that we drew up above, but around this coil. And this is useful because we can turn this magnet on or off by giving it electricity or cutting off the supply. We can activate it with a switch. All right. So now that we know about electric current and electromagnets, we are going to do electrical induction. Now this is the coolest thing that we can do with electromagnetism. This is how all of our generators work. So any way that we're able to make electricity, it comes from electrical induction. So you'll notice down here we've got a bar magnet and we've got a coil. So this is kind of going to be the flip side of the electromagnet, where instead of using electricity to create a magnetic field, we're going to use a magnetic field to create electricity. So when a magnet is moving through a coiled wire, it can cause electricity to start flowing. Okay. So in our picture here, this magnet has to move through that coil. So we need to take the magnet, move it through the coil, and as we move it, this coil is going to start generating electricity. And then we can take that electricity and bring it to our houses or our stores or anywhere that uses electricity. This is ultimately where it comes from, is moving magnets. I do want to make a little note down here at the bottom. This only works when the magnet is moving. So if we move the magnet inside of the coil, it's not going to generate any electricity if we leave it still. You have to keep the magnet moving through the coil in order for electricity to be generated. So in the next pages, you guys are going to be doing a PhET that explores electromagnetism. So you'll look at some electromagnets, some basic circuits with electric current, and electrical induction. So the link for that PhET should be in Google Classroom for you guys to work on for the rest of class here.